and comparing, selecting components, all of these things, systems, all of these things involve design. Design is naturally top-down. We've got a big problem we want to solve. Now, every once in a while we think of a neat little thing of where can we apply that. That's not the kind of problem we're doing now. We're starting off with, all right, we want to understand how are we going to measure edge sharpness better, or how are we going to make bamboo bikes. So it's a top-down problem. We start with the big functions. So what we do as engineers is we create value by thinking. So what is thought? Everybody agrees? So engineers do design. Design is about thinking. Because when we get practicing engineering, for the most part, what we're doing is we're doing the design and then passing it off to some other poor person that actually has to make the thing. Right? We have fun making things too, but there are people that go to trade schools and learn how to make things. And often we're organized and, all right, I designed it, now I give it to the guys on the factory floor and they have to make it. So I'm sort of the lazy one. I'm not going to get down there and make it. I get to stay in my air-conditioned office and do my stuff. More and more the factory floors are air-conditioned too. So what is thinking? We're going to create value by thinking. What is thinking? So this is a question that Eric, go ahead. Yeah.
I don't actually have an answer. Honestly, that's it.
All right, well, we're going to find out. You ready? Thought is all about semantics. We work in symbols. Thought's about manipulating symbols. And so we want to do just what Newton did. We want to capture and exploit the compact structure of the world. Somewhere I heard that Einstein said that all thought is pattern recognition. So that's what we're trying to do, is find the pattern between the way the lights move around the sky at night and apples falling on the earth. What are the patterns? And can we find the patterns? What's common to all good designs? So thought is all about semantics. So, like I was saying, physics is a short list of laws that predict many phenomena. So axiomatic design is a short list of rules for telling good designs from bad ones at all stages. So semantics. So we think about semantics lots of times in writing, but writing is about thinking and putting it down on the paper. So there's kinds of meanings, relationships, structure to the arguments, syntax, integrating elements into a meaningful entity. That's what thought is about, and that's largely what we're doing in design. So how can we apply these things? So we need an appropriate symbolic language in design. And then what we want to do, just like in any math problem, right? We try to reduce the problem to mathematics, manipulate the symbols, and solve the problem symbolically. It's so much easier than solving them all physically. So, lots of times you say, how do you tell a good design from a bad design? And people will say, well, simple. And they have the acronym there, KISS, keep it simple, stupid. But is that sufficient as an axiom? Can we use that? The problem is, if I say, all right, my job is to evaluate aircraft carriers. Which one's simpler? How do I do that? Or even take something even simpler than an aircraft carrier. We're going to go out and buy a lawnmower. Most of us don't have the opportunity to buy an aircraft carrier. Those are expensive. And then, where do you keep it? Lawnmower, though. Let's say you're going to go and buy a lawnmower. How do you decide which lawnmower to get? So is this self-consistent? The problem is, it kind of isn't, because trying to apply just simplicity like that isn't so simple. So what I need to do, whenever I get a problem that is too big to solve all at once, we decompose it. Break it down. Break it down until the solution is obvious. Figure out a good way to break it down. Just like you're going to have a nice big steak, you can't get the whole thing in your mouth at once. You got to cut it up somehow. And you have a system for cutting it up. Some people do like this, and they come up with little squares. Some people cut up a little square here. There's different ways of decomposing things. But you can't fit it all in your mouth and chew it at once, so you need to decompose it. Solving problems, same thing. You can't get the whole thing in your brain and chew on it at once, so break it down into smaller pieces. So the whole thing comes down, and what a lot of people look at the axiomatic design method, which involves decomposition, and forget what the whole thing really comes down to is two axioms, two simple laws. Now, I've been teaching axiomatic design here just about since I arrived, almost 25 years now. And about 10 or so years ago, I was asked to write a paper on teaching axiomatic design. I tried to get in touch with as many students as I could who had taken the course, and a lot of them are taking one of my courses on axiomatic design. And it was neat to see how many not only remembered that they'd taken the course, but were using axiomatic design. Most of them qualitatively, and most of them using just this, and said, just keeping things independent. I got my first patent this way, I saved the Navy $200,000 on this job we were doing, and just keeping things independent. So, and I would actually, I want to edit this. And the reason I'm doing that, maintain the independence, because as we do the decomposition, and I'll show you in a moment, at each step we want to make sure we're maintaining the independence. And that's actually the way Sue stated it. Lots of times we're going into an existing design and then we're trying to maximize the independence inside the existing design. But we're going to have the opportunity to start fresh, so let's maintain the independence. Because we want the design to be controllable. We want to avoid unintended consequences. And then minimize the information content. So an adjustable, controllable design without unintended consequences means that I can sort of change one thing without changing another. That one program can crash on my computer without crashing the whole thing. That I can change, for example, direction in the car without automatically changing the speed at the same time. When I was in college, I had a motorcycle that had been in an accident before I got it. And the front forks were bent, and so the accelerator's over here. So when I went to take the driver's test on it, you have to go very slowly around these cones. Most of the time when you're turning a motorcycle, you're just leaning and you're not really moving the handlebars that far. So there was a kind of unintended consequence when I went to take the driver's test, because all I had to do was just hold the handlebars like this and I went straight, which wasn't too much of a problem, and the motorcycle was cheaper that way. But when you twisted it, then the accelerator cable shortened up, and oh. So on turns to the left, acceleration was coupled with change in direction, which made it a little tricky going through the cones. Somehow I got my license anyway. But that's an example of a bad design, unintended, admittedly. I got it from Steve Blajewski in North Adams, Mass, and I'm sure it wasn't intended. Anyway, it went on, it was a Triumph 500. The next guy who got it was an engineer and actually fixed that. All right, he's a mechanical engineer. Minimize the information content. So what's that about? Well, usually we like information because it tells us what we need to do. In this case, we're using information as kind of as complexity. Think about it this way. If I have to give you a lot of instructions to do something right, the chances that you'll forget one of these instructions or misinterpret it goes up with the number of instructions. And so the more I have to explain stuff to you, the worse it gets. So here's only two things you got to remember. You can remember these two things. Actually, if you just remember the first one, you can do an awful lot. You can do designs better than an awful lot of people, and it applies to almost anything. But if I can minimize the information, then it's more robust and maximize the chance of success. The tolerances aren't so tight. And how do we design things so they don't need tight tolerances? So the guy who thought this up was Nam Su. He was, when he thought it up, he was a professor at MIT. This was about 40 years ago, and in the 70s. And he ends up being department head there and then director of engineering at the NSF. I should change that. He just retired a year ago as president of KAIST. He has an honorary doctorate from here. His first of many honorary doctorates, I think, was at WPI. He's now retired, lives in Massachusetts. KAIST is the Korean Advanced Institute for Science and Technology. Two big projects there. And I sent you all a link to a video. And if you haven't had a chance to watch that now the term's over, I recommend you do that. And if you're watching this, how many people watched the video of me? A couple of people. So this is kind of redundant, right? You've seen some of these. Sorry. Is it still worth watching me, or you haven't fallen asleep yet? Okay. Thanks for bearing with me. That was presented in a slightly different context. All right. So here was his premise, that it is design is a science. And there's 3 books. These are kind of expensive. They're in the library. I do recommend them. I had to read this one 3 times before I felt like I was ready to teach from it. So I try to digest this stuff and help you. There's a lot of neat case studies in this. Anyway, one day Nam was here giving a lecture, visiting lecture. The place was packed. The president was here. Nam showed up late. And one of my students asked him about this book, and he said, I never intended this as a textbook, and I was using it as a textbook. No. If you never intended it as a textbook, why did you put problems at the end of the chapter? Come on. You made a little support here now. All right, how do we tell a good design from a bad? I don't know how many of you have been in design groups, but quite often what happens is, and people naturally fight to keep their design, their aspect, their one, their thing in the design. It's like you're fighting for your genes in the next generation, and you'll do it. Yeah, you'll defend your children beyond all rationale. That's intended. That's a good thing for evolution. But in design, what we need is an objective set of rules. So yeah, you always like your little addition to the design, but what we need to do is sort of set up some objective criteria that beforehand, and we're all going to agree that this is the way we tell if it's a good design. So we can applaud somebody else's efforts and support those when it's appropriate. And we'll know how to argue for ours or theirs based on what we're going to be discussing right now. And I can't tell you that without this, how long and unproductive the discussions can be when people are really just trying to defend their part of the design. Do you agree?
Yeah.
When I teach this, and I started teaching this to my grad class, it's about half people working in industry and half full-time students. And it's nice. I can always, without exception, always get support from the people working in industry. That yeah, that's the way it works in industry. We have long arguments. So Mike Schapolsky, 3 degrees from WPI. I think I meant to put his class years up there after the apostrophe, forgot to. Also an All-American baseball player. And yesterday, so he was one of my students, he was my first doctoral student here. And then he went to GE Corporate Research and says, yep, this takes us from argument to analysis, evaluating designs. So he's now the head engineer at Hypertherm up in New Lebanon, New Hampshire. And so they're one of the top 500 companies to work for. It's pretty neat because Hypertherm is a kind of snobby Ivy League kind of place up there by Dartmouth College. And they recognize that Mike brought a lot of value in doing stuff. The other neat thing is that his son was here yesterday trying to choose between WPI and UNH. Although this is kind of scary, now I'm getting the children of my initial students. So axiomatic design, this is kind of the grammar of design. So you can get somebody that knows grammar to edit what you're doing, and I do that frequently actually. I'm not a very good proofreader or editor, and I've got a friend who's a professor at Becker, an English professor, and she goes through and edits my scientific stuff and improves the writing. She doesn't have to know the science. So if you know axiomatic design, you can step into any design problem. And one day, about 15 years ago or so, Nam and Sue called me up and said, we need you to help with this design problem. And I want you to bring some grad students from WPI, and we're going to work on designing the crew safety system, the crew survivability system in the next orbital space plane. It was a pretty neat problem, and it was like the problem of the decade, he called it. It was until the government cut the money for the next orbital space plane. And then Bush said he was going to Mars. We were hoping that he was going to go. We were disappointed, of course, that the orbital space plane was cut, but we learned a lot in designing this stuff for it. And we'd like to see more funding of the space program.
I want to go on the record, I like them.
Okay, good. And the space program still isn't getting the funding, so I don't think it really matters who's doing it. I just got some pieces from NASA to look at, some additive manufacturing pieces. They couldn't pay the postage. We had to pay the postage. It came in a box that had obviously been recycled from like a gift or something. They released nice metal additive manufactured parts. When we were working with NASA, actually they reported our funding is so bad we don't have money to buy toilet paper for the bathrooms. I said, in those days we were using fax machines a lot. They go, we have toilet paper here, we'll fax you some. All right. And that was under that other guy there, what's his name? Willie, Slick Willie. Anyway, Clinton, there we go. All right, let's get out of politics. So the point was, I said, no, I've never worked on spaceships or space travel before. He goes, doesn't matter, you know axiomatic design. That's all you need to do. That's all you need to know. And you can help us with that. And it was neat. Actually, after they canceled the orbital space plane, started working on the Mars mission. I actually got in to sit on some of the initial meetings for designing the Mars mission. And I learned a lot by doing that, and I was able to help them. And we haven't done that either. So what's the state of the art in engineering design? It's an algorithmic approach. Basically, it assumes that if I do it, if I use the right process, I get a good result. It requires iteration. And so there's a bunch of trial and error. And if you look at the traditional books on design, They have the circle. It's like designed in sort of iterations. And the ideation, testing, prototype, revising, and we want to get out of that. We want to go in a straight line, not in circles. And how do we evaluate it? Well, we need somebody that's had some experience doing this. And that was what I was saying to Nam. We don't have any experience doing this. It doesn't matter, you know, axiomatic design. We want you in here. So axiomatic design, we've already seen the axioms. It requires decomposition. We talked about that already. We'll go into that a little bit more. And then we evaluate by sort of rules in the decomposition of the axioms. Now, axioms are just kind of rules. And the axioms can't be proven, they can only be disproven. And that's one of the things I invite everybody to do, and it's a good exercise, and I've done this every year I've been teaching this. Let's see if we can find some violation of the axioms. Let's find a good design that doesn't follow the axioms. Right? So this has only been around for about 40 years. Newtonian mechanics has been around for over 300 years. You can't prove F equals ma, you can only disprove it. And I mean, you could set up some experiments, and go, oh, it's consistent with what I just did. Here's another F equals ma. But you can't, like, sit down and prove it from what? Okay. So, all right. So just like if we want to solve a force problem, we need to decompose it, we need a structure. We need a structure and a process to create it. So here's what I've done for teaching axiomatic design, to decompose it. So there's three elements. So we have the axioms, which you already seen, structure, which we started to discuss, and then the process for creating the structure. So I decompose it into three elements. And you know those three things, you got it. So, and then, and I like maintain the independence better. I've changed my mind since I did this, so that should be maintained. And then we've got two kinds of decomposition, horizontal and vertical. We'll talk about those in a moment. And then how do we do this? We zigzag physical integration, and we'll get to that. So the horizontal is into domains. So customer needs, and that's what we're talking about. What do you need? What adds value? What would make this project valuable to you? Certainly graduation is important because you get the degree and you're worth a lot more in the marketplace. But there's other things that you want to get. The ability to do designs better will make you more valuable if you're working for yourself or anybody else. And you may need to learn how to present this to your spouse so you don't drive them nuts. No, it's Smiley's axiom too. We're not going to do it this way. Let me tie this stuff on the top of the car. There is probably another objective that is more important than tying the stuff on the car when you're dealing with your spouse. Functional requirements. Unless you're smart like Wally and you marry another engineer.
My whole world is FRs and TPs.
Yeah. And you couldn't have married better. Anyway, functional requirements, FRs. This is what it does. So what adds value? So what does it need to do to add that value? So that's what we want to do. We want to collect your needs for this project, and then we want to figure out what we need to do in kind of engineering terms. And there's going to be some rules that the functional requirements have to follow. Then, what does it look like physically? What things like that go on a print? And then, how do we make it? How do we get it to come back? So the two most important parts, probably functional, physical. Nam calls this bimodal thinking. Nam also does a lot with manufacturing. I like to think of trimodal thinking, functional, physical, process. But it's the functional needs that get us started. Now, there's also things we need to worry about, constraints, things that need to be avoided. And we'll see what those are. So, as I said, this basically boils down to the two things that we really want to focus on. We'll be focusing on for the next few minutes while we finish this up. Functional and physical. Bimodal thinking. What does it need? What does it need to do? And what does it need to look like to do that? And that's something you may not have been doing. In other words, lots of times we kind of confuse the solution and the problem, and we don't see them clearly as separate things. We need to define the problem in a solution-neutral environment so that we're not jumping the gun on the solution. And that way we open up the solution space and we can see many more possibilities. Figuring out what it needs to do first is important. Let's figure out, if we don't know what it needs to do, if we don't know what it is it's supposed to do, we won't know when it's doing it. So the FRs define success. If we do the FRs, because we carefully figured those out from the customer needs to make sure we satisfy all the customer needs. So the FRs are the functions that define success. So we got to provide the desired function. So design is about solving problems. This means changing something. So the FRs define what needs to be independently adjustable. So I need to be able to change direction and change speed independently. And adapt to the change. And capable of providing the change. All right, here's an example. So some of you might have studied American history and remember the Civil War, or remember studying the Civil War. I was very young at the time. So some interesting technology gets developed in wartime. And lots of times in the North we call this the Monitor versus the Merrimack, because the Virginia was the Merrimack, and it was a Union ship that sunk and got rechristened the Virginia. But when I studied it, it was the Monitor versus the Merrimack, and I kept wondering, the Merrimack is a southern ship. Why did they name it after a river in New Hampshire? And it was the Union that named it after that. So in our biased study of the Civil War in the North, we don't recognize the rechristening. In case some of you are from south of the Mason-Dixon line, I'll try to remember to call it Virginia. So there's a neat thing about the breakthrough in the design. And there's a couple things I want you to remember from that we should notice in this picture. So this is the Virginia. And this little one here is the Monitor. And I think, let me see which set of slides I have. All right. So the Virginia got a bigger motor. So it was a sailing ship like these ones in the background. Got a bigger steam engine, and it's faster. It's got lots of guns. And so the South raised this. The North knew what they were doing. It's an ironclad ship, so it doesn't rely on the wind to get it around. It's already decoupled locomotion from the wind now, so we can drive around. And so there's kind of a race. The South is getting this going. They've got to they've got to break the blockade, because the North is blockading the South and keeping them from trading cotton with the British and getting arms from the British. And this the Monitor's being made in New York City. And the big deal here is that it's got independently adjustable direction of fire. It's got a swivelable turret. And so this was Ericsson's design, a Swedish guy. So, as I said, steam decouples the locomotion and the wind, and then a swivel turret decouples the direction of travel and the direction of fire. And so there's a new FR. So how do you make something neat? You come up with a new functional requirement, one that somebody hasn't thought of before. Up until then, the guns moved to the ship. I wanted to change my direction of fire. I had to say, come about, over the sails. All right, now shoot. The Monitor's just, so I want to maximize the independence of the functional elements. So one of the things we noted, all right, so what happens in this? On March 8th, I guess it was, if you read the history of this, if I understand this right, the Virginia gets out into Hampton Roads, which is a funny name for a wet place, but and it starts, just goes out and starts basically sinking Union ships at will. It's ironclad, you can outmaneuver them, it's got steam, it's got lots of guns, and it just starts sinking the Union ships, and it looks pretty bad. So they're hurrying to finish the monitor. Its sea trial is the run down from New York City to Hampton Roads, and it arrives the next day and neutralizes the larger, faster, more heavily armed. And we can see here that it's sitting 45 degrees, and I can't tell if this is the bow or the stern. I don't know where to fly. It's 45 degrees up here, which means that it doesn't have any guns pointing at it, right? And it can point its gun at, it might have two guns in that turret. This so frustrated the captain of the Virginia that he accused the captain of the Monitor of not being a gentleman. That's a big deal if you're from Virginia, but if you're from New York City. Anyway, I wasn't a gentleman anyway. That's a big deal.
This is my most favorite slide of all the slides you have.
Yeah.
That we owe the existence of our current American government to axiomatic design. Based on this.
I don't know if this was really the decisive battle of the Civil War. Anyway, so let's take a look at it this way. So we're going to be looking at these matrices. So here are the FRs. These are the things that we wanted to do. These are the DPs. This is how it gets done. So we make up this little matrix, and so the Virginia looks like this. Adjust the direction of travel, adjust the direction of fire. We got one thing, basically, one control, the rudder. Right? Go, yeah, 20 degrees up, right? Now, so that's what we call coupled. It lacks independence. The monitor's got two DPs, two physical things now. And we'll see that we really need this to decouple things. So things can't be independent if I've got one DP trying to take care of two FRs. So we get the rudder, and now we get the turret. So adjust the direction of travel with the rudder. Put an X there because there's influence. The rudder influences the direction of travel. The turret does not. We put an O there. The turret, however, adjusts the direction of fire. Put an X there. Is this right? Is it missing anything? So we put an X where there's an influence. So what about here? Does the rudder influence the direction of fire for the monitor? Right. So there's a mistake here. Let's see, I already said each FR requires a DP, and there we go. Oops. Is this correct? There we go. So that's the way it should look. So what this means is, with this system, until I have a computer on board that can sort of keep track of things and simultaneously, when I change direction, keep the thing firing in the same direction. So when I change direction, I have to change direction of the ship. I've got to adjust the turret, but first I get the ship going the way I want it to, and then I adjust the turret. If I adjust the turret first and then change the direction of the ship, then I'm not shooting in the right place anymore. So a diagonal matrix is the best, but a triangular matrix will work, but it gives me an order in which I have to make the adjustments. So it's neat. I said we were going to figure out some symbols for design, then we could manipulate the symbols and find some of the solution. Now there's many existing designs that will work fine if we know the order of adjustment. But because nobody's made the matrix and solved the thing and used some linear algebra to see if it can be adjusted into a triangular matrix, it seems very complex. In Anamsu's book, he calls this artificial complexity. It's not really complex, you just don't know the right combination. Anyway, innovation. So one of the neat things we want to do is innovate. And so where does change create value? What are good new functions to have? And how can we improve the independence of the functional elements and reduce the information content? So there's two things that are really important, really important. We still have a lot of poor people in this country and on this planet. There's all kinds of things we could be doing better. And so what do we need to do that? What do we need to raise the standard of living of people? Innovations and productivity. And we really need innovations to improve productivity. And so here's our job. We're engineers. We gotta figure out how to innovate. Innovate for the sake of getting stuff done better, like how can we make a better bicycle cheaper and improve productivity? How can we make it faster? So, and it's not just bicycles. That's what you're signing into as an engineer. All right, so here's another example. So this was taken before they redid the beautiful washroom on the second floor of Washburn. So it's much nicer than this now.
What are you talking about?
You haven't noticed how much nicer the sinks are? I don't know why.
That's been there since 1963.
This is not the same sink that's there now.
Really?
Really. Well, Professor Towner is verifying this. Let's take a look at this. Is this a good design? No, why not? Couples, right. And you've seen this before, somebody. For those of you that haven't seen it before, can you tell right away it's not a good design? Well, actually what we need to know is what does the customer want? And who is the customer? Now, there are some places, and you can still find these funny old places, where the customer is not the person washing their hands. They're the person that is running the rest area or something. And in the old days, the biggest customer need was not to have the sinks flood. So they had these spring-loaded faucets, right? You push it down, you get the water out.
When did they do that?
Like you haven't paid attention to it. So in the old days, you had this thing, if the customer is the one that says, my first need is, I don't want these things to overflow and make a mess. People are throwing the towels in there and like